Well, welcome to another episode of Old Guy Physics. And this lesson is going to be on something called an Atwood device. Atwood device. Now, an Atwood device, for the most part, contains a pulley. Okay? And it'll have an object hanging off of one side of the pulley, and it will also have an object hanging off the other side of the pulley. And so if we give these some values, let's say that this is a 1 kilogram mass and this is a 3 kilogram mass, and they're attached together by a string or cable or whatever that comes over the top of the pulley like this, then there should be some things that are logical, that are commonplace type things that don't require you to be a physics person, but it should just make sense. First of all, if this is 3 kilograms, then there's a force of 30 newtons pulling down on that particular block. On the other hand, if this is a 1 kilogram weight, then there should be a force of 10 newtons pulling down on this side. Well, right away you can see that this one's heavier than this, and if allowed to move, if the pulley has no friction, has no resistance to movement, then the moment that you let go of this, you would expect the 30 newton box to come down towards the tabletop here, and the one that only weighs 10 is going to go up in the air. And that makes pretty good sense. Now, one of the questions that they're going to ask you is, number one, what's the acceleration of the blocks? And it's a little more involved than just going, oh, it's this. You know, it's going to require some math, and we'll talk about that in a second. And secondly, they're going to ask you, what's the tension on the string? Now, let's talk about some more stuff that makes sense. If this 30 newton box is going towards the tabletop, then the tension, the T right here, is fighting against this 30 newton force, but it's losing. In other words, this one's moving towards the tabletop, so that tension is going to be less than 30. Okay? Likewise, this 10 newton force is pulling towards the tabletop, but as soon as we let go of it, there's going to be a tension right here. And we know that it's going to be greater than 10. Because the string is pulling this block up as this block is pulling the string down. Now, one of the things that we know is that the tension here and the tension here will be the same because it's one continuous piece of string that's attached to the two blocks. Now, there is an easy way to do it, but I'd like to go ahead and show you the mathematics that you're supposed to understand in order for this to work properly. Now, on this problem, the net force is going to be, and I'm going to use capital M because that's the larger force, so I'm going to put a little 1 right there, mg minus T will equal, let me write that right, capital M A. Because the force of the weight is greater, and we want a positive difference, than the tension, and that overall mg minus T will give us the acceleration of the larger block. Likewise, if we write an equation for what's happening with the smaller block, we've got T minus small mg, and I'm going to put a little 2 right there, is equal to little 2a. Now, this is showing that the tension is pulling up on the smaller block, and again, we're going to end up with a positive difference. Now, the things that we know about these two equations is that number one, the tension should be the same. And likewise, the acceleration should be the same. But we have two equations and we got far too many variables for us to be able to solve that with any success. Now, as I showed in class, and I'm going to show you again, I think that I always called it simultaneous equations. It may be called other things with a different math teacher. But what basically I'm saying is I'm going to solve for t in this bottom equation, and then I'm going to substitute it into the first equation, and by doing that we eliminate the letter t in the equation altogether. So let's look at this first equation. I'm going to add m2g to both sides. And that one cancels. So now t is going to be equal to m2a plus m2g. And those are lowercase. Now, if that's what t equals, I'm going to take that quantity and I'm going to substitute it back into my original first equation so that I have this information substituted in where the letter t is. Let me change color so it makes it a little easier to see, perhaps. So, I'm going to take this equation, I'm going to write it right here, capital Mg minus the quantity M2A plus M2G equals capital M1A, like that. Now you can see that the t's are all gone. So now I want to distribute this minus sign inside the parentheses, and so I can take away the parentheses like this, and when I take that away, this sign becomes negative, or it's a subtraction just like the one that was outside the parentheses. So you got M1G minus M2A minus M2G equals MA. So let's combine some terms. I'm going to add M2A to both sides, like that. This one cancels, and if I rewrite the equation, it's going to be capital M1G minus M2G is equal to M1A plus M2A. Now, you'll recall that back here that we were going to try to solve for the acceleration. Well, that means we need to isolate the A over here by itself, and you can see that there's an A in this one, there's an A in this one. So we could rewrite this to be capital M1 plus lowercase m2 quantity A. In other words, I pulled the A out of each of these to make it look like that. And then I can divide M1 plus M2 quantity to the other side, M1 plus M2 quantity. This one cancels, leaving the A by itself, and now we've got M1G minus M2G over M1 plus M2. Now, you can see right away, or maybe you can see it, that this is the weight of the first object minus the weight of the second object divided by the sum of the two objects. So I'd like to stand saying that this is the mathematics that gets us to the answer that we're looking for. But there's an easier way to state this, and we're going to say it's the difference of the forces divided by the sum of the masses. And you can see the difference of the forces. You got the weight on one side, you got the weight on the other side. That's the only two forces that are acting over there. And then we've got the sum of the masses, and that would be the mass of each of the blocks that are on the string. So if we do that, it's going to be 30 minus 10 over 3 plus 1. And that's going to be equal to 20 over 4, which is 5 meters per second squared. Does everybody see that? Now, once you have the acceleration, we can come over here and say the acceleration now is 5 meters per second squared, right there. Well, now we can take either the top equation or the bottom equation, substitute in the acceleration. Let's plug it in here. The 5 goes here. We know that g is 10, so we've got 10 plus 5 equals, and the tension's going to be 15 newtons. Now, remember what we said, that the tension has got to be less than 30, but it's got to be greater than 10, and 15 falls between 30 and 10, so it appears that we have the problem right. Now, this is the beginning of solving for Atwood devices. In the next video, I will show you how we do that on a flat surface with pulleys acting in a certain way. We can put a pulley on an inclined plane. There's any number of these kinds of problems, but the key factor is that there's a pulley involved, and it involves a set of equations that accounts for what's happening with this one and what's happening with this one. If you have any questions, see me in class, and like always, have a blessed day.